Alrighty, guys, so real quick, just move some stuff. So what I want you to do is have your notes out. You should be on page 7 of your notes if you have the notes that I'm showing on my tiny screen now. Page 7. If you don't have those notes, remember, guys, if you go into materials, let me just go into class, sorry. Wait for it to load finally. So you just go to digital notes. You can do these on Kami, or you can do these on Google Docs if you don't have those, because you can just keep opening that every time, right? So it's just going to keep in saving your information. Anyway, let's get into it. So I'm going to go ahead and hit present. So you should be following along right now on page 7 of your notes. Okay, so these are the steps for drawing free body diagrams. We learned the forces just a moment ago, right? So let's just talk about this. You're going to make a box that will represent the object and the forces acting upon the box. So the box, this is typical in introductory level physics. We don't draw the actual car or a tree or whatever. We just draw a box. So remember that the arrows are the same size. Either the object is moving, is not moving, or moving at a constant velocity. That's super important. Remember, force is a vector, meaning direction matters. The size of the arrow matters. So a tiny arrow means a tiny force. A large arrow means a large force. So if the object is resting on something, you have to draw that support force, or F sub n, or the F normal. Or you can put F norm or F sub n. I don't care, right? As long as I can tell that there's an n there. That means that's the support force. That's what I call it, the support force. So first step, draw your box. So that's little g, because we're on Earth, right? That if it's resting on something, that's the support force. So the red arrow is the F norm, the support force. The F of little g, anytime we're on planet Earth, we're going to have F of little g, 9.8 meters per second squared, the acceleration due to the force of gravity. So all of that should be written down underneath number 3. You should have filled out the words that are bolded, right? You can pause the video if you need to, right? If you forgot to do that. If an object is falling, you do not have to draw the normal force, right? Because remember, the normal force is the support force. So right now, my hand is the support force for the paper. I take away my hand, it's falling. It's F of little g. So depending on the problem, you may have to include air resistance. So in this one, and this probably isn't drawn to scale because the air resistance is very, 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 very minuscule and tiny, typically, right? Typically. So F of air, or F of air resistance, the force of air resistance. Okay, so that's going to show me, if I look at this, I know that the object is going to be accelerating downward because the F net, if I did vector addition with those, okay, so notice that the size of the arrow is larger for F of little g, the black arrow, than F of air resistance, the red arrow. Therefore, the object is accelerating downward. Now, remember, acceleration can mean 3 things: speeding up, slowing down, turning. So we're just going to say accelerating for now, because there'll be some exceptions to this moving forward. F of little g is much greater. So if I do the tail to tip method, right, I can only put my second arrow, start my arrow on the end of the first arrow. Notice that my F of little g is going to be much bigger. So my F net, my overall, is unbalanced, and that's why it is accelerating downward. Remember, accelerating can mean speeding up, slowing down, or turning. Okay, so this is all the stuff you should draw. So you can pause the video now. That should be drawn in your notes right here on number 5 at the very bottom. So that should be done. So now what we're going to do, okay, there's answers to this. This is on, if you're on page, so we turn our page to page 8 of our notes. So you can check your answers on Student Resources, Unit 2, A14, if you want to. And there's also a link here in the PowerPoint, but you guys can't see it because it's a video, right? So anyway, so I'm going to do the first one for you. If you get them wrong, it's okay. I don't want you to look at the answers. Yeah, you can just copy them, but are you learning if you just copy? Some of you maybe, right? But like a book is resting, so a book is resting on a tabletop, right? We're going to draw the forces acting on the book. Right, so this is a pretty simple one. We're going to leave out any calculation. We're just drawing it right now. Jamboard. Come on, Smith. You're recording this. This is going on the internet. Is it this one? Yeah, okay. So what first step is I just draw my arrow. I'm on Earth. We're going to, unless I say otherwise, assume you're on planet Earth. Okay? Assume you're on planet Earth. That's a pretty crappy box. I could have done better with that. Since we're on planet Earth, force of F little g. Now, if I gave you the mass of the box, you could do the mass times 9.8 to give you the actual force, and I could draw it to scale, right? But we're not going to do that as it's starting out. So since it is not moving and it's at rest, it's sitting on something, I'm just going to write the other one. So let's see. 1, 2, 3. 1, 2, 3. Okay. See, I made it the exact same size. That's my normal force. You can put norm, F sub n, F sub capital N, F normal. Any of that works. Okay, that's the correct free body diagram for this. So I know by looking at this, since the support force is there, the object is not moving. Okay. Now remember, if they're the same size, it can mean two things: either not moving or moving at a constant velocity. Because don't forget, F net equals m times a, right? So if I have a balanced force, I'm either not moving or moving at a constant velocity. If I have an unbalanced force, that means that this is greater than 0. This number right here is greater than 0. That means I have to have some form of acceleration, right? Because if I'm going at a constant velocity, this number for acceleration, you have 0 acceleration if you're going at a constant velocity. Acceleration, in case we forgot, almost done, guys. That's what that equals, right? So if I'm going the same speed, my final velocity minus my initial velocity is going to be 0 right here. So then if that's 0, that's 0. If that's 0, this whole thing's 0. So this is something that's a common misconception I see with students. If the arrows are the same size in a free body diagram, it could mean the object's moving at a constant velocity. So don't fall trapped to that, okay? If you have them different size arrows, you know you must have acceleration in some way, shape, or form in that direction. Remember, acceleration can mean 3 things: speeding up, slowing down, turning. So you're going to practice this doing the rest of those practice problems there.
Go, hit it. Oh no, are you serious? No way. Are you serious?